Okay, now we're going to take a look at another process that doesn't head off to infinity but remains within finite bounds, and that is logistic growth. And we've seen that in earlier modules. We've already come across it with its sigmoidal or S-shaped growth curve. So suppose we have a process that tends to feed on itself, like population growth or the spread of a disease. So the more people there are, the more babies are born and the faster the population grows, or the more people are already infected with the disease, the more those people tend to infect others, and so the faster the disease spreads. And we know that a process like that obeys an equation of the form x dot equals rx. The rate of change of x with respect to time is equal to a constant times the existing value of x. So if this is a population, the population grows in proportion to the size of the existing population, or the disease spreads in proportion to the number of cases already infected. And we know that the solution to an equation like that is an exponential. In principle, that would just keep growing to infinity. But in reality, it can't grow to infinity because with, say, population, there's only the capability to feed so many people, and the population can't grow beyond that. The disease can only infect the entire community or the entire population. But once everybody's infected, there's nowhere more to go. So there will typically be some kind of ceiling to the growth. The growth is capped at some level, which we could call x max. So what will happen? Well, possibly the exponential growth will just keep going up till it kind of collides with the ceiling, and then it will stop and maybe just stay at that level or something. But what actually happens is that as you get closer to the ceiling, the growth starts to slow down, because if you're approaching, for example, the limits of what the food available can support in terms of population, then people start to feel the pressure. They feel poorer and they're less likely to have babies. And so the population growth doesn't keep accelerating towards that point, but already well before you reach it, people are reducing their propensity to have babies, and the population growth rate is slowing down. Or if it's the disease, as it's approaching infecting the entire population, there are the people who haven't yet been infected are increasingly rare, so it's increasingly difficult for the disease to find them and jump to them. So instead of this kind of hard collision, you'll get a soft landing. It turns over and goes like that. And this kind of process is found in a whole range of socio-historical scenarios. For example, it's been shown in religious conversion. The conversion of a country to a new religion tends to follow a logistic. The spread of a technology, at first there are few people, then it catches on, it becomes more and more popular, spreading, but then almost everybody has it, and it reaches saturation. And you can also see this in the personal productivity of great scientists, for example. At first they produce a few papers, then they go through a very productive phase, and then their output tends to tail off. The same with a cultural movement, like an art movement, Impressionism or something. At first there are a few people working in that new movement, and then it catches on and more people join the bandwagon, and then it loses its popularity and it tails off again. And so the output of new works has stopped, and that you've reached pretty much the limit. So what we want to do is have a look at the mathematics behind this, so that we know what we're looking for when we see such patterns in theoretical history, what models must lie behind it. Okay, so starting with our exponential, we have we just seen the rate of change of x dot is equal to a constant times x, and this is the growth rate r, and it's going to be a certain percentage per unit time of the existing value of x. And we said that the solution to that is x equals x naught e to the rt. It's the exponential growth, and x0 is the value at time 0. Well, we said though in this logistic growth, remind us we're looking at that, the logistic growth, that the growth rate is going to decrease, it's going to slow down. So instead of it just keeping on growing, the growth rate decreases and eventually reaches 0 as it sort of plateaus here. So what we imagine is that the growth rate r varies with the value of x, and when x reaches its maximum, x max there, the growth rate will be 0, stops growing. So if r starts at its maximum value when x is 0, so there's no obstruction to growth, it can grow fully exponentially, but as x increases, the exponential growth finds it more and more difficult to continue, and it will eventually start to turn over. So the growth rate is decreasing, and when it reaches x max, it's 0. So that's kind of the simplest possible assumption about how the growth rate varies to produce such a curve. And the equation here would be r equals, r, the growth rate in the equation is going to be r some constant times 1 minus x over x max. That's the equation of this straight line. So you can see that when x is 0, this is 0, so it's r times 1, so it's just at r. And when x is x max, this is x max over x max, which is 1, so it's 1 minus 1, which is 0. So r goes down to 0. And so, and between the two, it's that straight line. So what we want to do is put this expression into our exponential equation. So it becomes r x into 1 minus x over x max. I just put the r in front. I just kind of separated that up just because it's kind of neater to have it that way. And this is the logistic equation. So if we see an equation like that, we know it's describing a logistic growth. And we can solve this equation, but it requires some sort of integration tricks, which I don't think is helpful to get bogged down in that, because we're not really interested in how you solve equations like this. We're more interested in the results. So I'll just go straight to write down what the resulting formula for x would be. It is that x equals x max times e to the rt over e to the rt plus c. And this c, in fact, we can work out what it is, because at time 0, when t is 0, this would be x equals x max times e to the rt, t is 0, that would be 0 there, so e to the 0, which is 1, ditto here. So that's 1 over 1 plus c. And if we call that x0, then we can rearrange this. We get x0 over x max equals 1 over 1 plus c. We can flip those, so x max over x0 equals 1 plus c, and therefore c is equal to x max over x0 minus 1. So c is our constant of integration when we solve this equation, and it depends on the initial value x0. Okay, now we'll just have another look at this equation and how we can get a better understanding of how it might apply to particular data. Oh, and I should say that although there is this solution to it, we're not normally interested in that. We're only interested in, we see logistic behaviour, we know that the system obeys the logistic equation. We're not, it's very seldom the one's going to be interested in the exact formula for this. It's more that what's of interest that it's logistic, and then this is how the variables interact to produce the logistic behaviour. The exact formula of the logistic curve is not really relevant to us. So let's write up again our logistic equation. X dot equals Rx into 1 minus x over x max. Now if we want to show that data is logistic, we can take our values of x again and time and plot it on a graph, and if it comes out sigmoidal, we know that our data is logistic. But it's a bit difficult to see by eye if it truly is. It might look vaguely sigmoidal, but it might be asymmetric or something, and it might not really be logistic, but it's just a sort of got that general shape. So what we can do is use a way of transforming this that means that if we plot our data, it will give a straight line if it is logistic. And it's much easier to see how well it fits a true logistic by seeing how closely it fits a straight line than it is by trying to do it by eye, looking at the raw data like that. So we're going to look at a technique for transforming and then plotting the data to make it so that it will come out as a straight line if it is a logistic curve. So the first thing we do is divide this through by x max. So we're going to have x dot over x max is equal to r times x over x max into 1 minus x over x max. And now x over x max as x max is the fraction of the whole logistic growth that has so far been completed. So when x reaches x max, this x over x max is 1. So it's done 100% of the growth. When it's somewhere around here, x is half of x max, so it's completed 50% of the growth. So x over x max is 0.5. So we can write this as the fraction f of the growth that has been completed, which will vary between 0 when x is 0, and 1 when x is x max. And then x dot over x max is just f dot. That's the rate of change of x over x max, because you can see if we do take the derivative of f here, x max is constant, so this just becomes x dot over x max. That's what we've got. So that's f dot equals r, and then we've got f, and here 1 minus f. And now we want to solve that equation, and that is what I said in the just now. You know, it involves some integration tricks and techniques which you know, I don't want us to get bogged down into. But I'll show you, you know, satisfy you that how this works. So we can take the f1 minus f to the other side, and we've got 1 over f into 1 minus f dot equals r. And what I'm going to say is that this is the derivative, let's put it here, whoops, 1 over f into 1 minus f dot is the derivative with respect to time of the log of f over 1 minus f. Well, we can see that by using our chain rule. So to differentiate that with respect to time, firstly we differentiate it with respect to f, and then we multiply by df by dt. That's a chain rule. So if we're doing d by dt of that, we can do d by df times df by dt, and the df's cancel. And now we can differentiate this with respect to f, because that is equal to d by df of, using the principle of logarithms, their logarithms turn multiplication into addition. This is log f plus the log of 1 over 1 minus f, which we can write as 1 minus f to the minus 1. So this is 1 minus f to the minus 1. So this is f times 1 minus f to the minus 1. So the multiplication becomes an addition of the two logs. So that's log f plus the log of 1 over 1 minus f to the minus 1. And then we know that when you know, log of x to the n is n log x. So this just becomes minus the log of 1 minus f. There you go. So this is d by df of that is d by df of log f minus log 1 minus f. That's just us rearranging this into two different logarithms. And then d by df of log f, we should remember from the work we did on the exponential, and times df by dt, of course. So d by df of log f is 1 over f. And for this, we know what log f is. We don't know what the derivative, or we know what the derivative of log f is. We don't know what the derivative of log of 1 minus f is. So we apply our chain rule. So we firstly treat that just as the variable. So with the log, log of x becomes 1 over x. So this will be log of 1 minus f will be 1 over 1 minus f. and we had a minus sign, so it's minus 1 over 1 minus f. But applying our chain rule, we've differentiated the bracket, treating it as a variable. Now we must multiply by the derivative of the bracket, and the derivative of 1 minus f, that constant becomes 0, minus f goes to minus 1 when we differentiate it. So we're going to get times minus 1 when we multiply by the derivative of the bracket. And we've got a minus there, we're multiplying by another minus, so in fact this becomes plus. Not sure why that's floating up there. Plus. So it's 1 over f plus 1 over 1 minus f. That's d by df of that thing. And that's multiplied by df by dt. So we've now got to put this over a common denominator. So we multiply this one by 1 minus f on top and bottom, and we multiply this by f on top and bottom. So it becomes 1 minus f over f into 1 minus f plus f over f into 1 minus f times df by dt. And now we can see over the common denominator, this is 1 minus f plus f over that, and 1 minus f plus f is just 1. So this becomes, up here, just 1 over f into 1 minus f. That's a simplification of that, multiplied by df by dt, which is, in other words, f dot, which is what we started with. So I said that this is equal to d by dt of log f over 1 minus f, and I've just shown you that indeed it is. So we can get rid of that. This, say we've just written, is just the d by dt of log f over 1 minus f, so we're going to put that in. This is what we've just shown, is d by dt of log of f over 1 minus f equals r. And now to solve this, we just want to integrate this. So integrating this side with respect to time is just, this is a derivative with respect to time, so integrating it with respect to time, we'll just get back to what's in the bracket there. So we've got log of f over 1 minus f equals, and integrating r with respect to time is just rt, and I'm going to put a minus sign, minus c. We know that r comes from differentiating r times t, and then it's plus a constant of integration, though for reasons that will become clear in just a moment, I put that as a minus sign. So you can see if you differentiate that back, you'll get r. And what is c? Well, consider the situation when the growth is halfway. So we'll call that t 1/2. When the growth is halfway, f is a half. That's a fraction of the growth completed. That's just what I've just said. So this will be the log of a half over 1 minus a half, which is also a half, equals r t1/2 minus c. And well, half over half is log of 1. So half over half is 1. So this is a logarithm of 1, which is 0. The logarithm of 1 in any base is 0. So that is equal to r t1/2 minus c, or in other words, c is equal to r t1/2. So this constant depends upon the time at which it is halfway, and it's just r times that. And you can see why I put it as a minus, because otherwise c would be a negative constant. So it just reminds us that this is actually negative here. And then the point of all this is we can compare this with the equation for a straight line, y equals mx plus c. And what we can see is that if this takes the place of y, so we plot log of f over 1 minus f against, this takes the place of x, so we're plotting that against t, then we'll have a straight line with slope r and y-intercept c, where c is given by that. So if we have some data that we suspect obeys a logistic curve, we can plot here log of f over 1 minus f against the time t, and if it is indeed logistic, we will get a straight line. Now, the only problem with this is that to calculate f, if we've got some data, so we've you know, what we're given is the x values. So we've got some data. We want to plot this thing. We need to find f. But to find f, we need to know x max. But you know, that doesn't necessarily come with our data. We're just shown what the x values are. So what we can do is kind of plot it and make an estimate for what x max is. More sophisticated, you could do some statistical fitting to find out what value of x max works best. So we've got to find some way of working out x max. Generally speaking, you know, one can estimate by eye where it's heading to get a rough values for f1 minus f, and you know, you'll see if it's pretty much along a straight line, then you know, you can believe that you're looking at something that is genuinely logistic. If it's not, it might be because you have chosen x max poorly and you could possibly adjust it, or otherwise, if you can't find an x max that makes it a straight line, then you know, it's not logistic. So the point is then that transforming our data in this way, instead of plotting just x against t to get something like that, we plot this log of f over 1 minus f, and then you see straight lines. And that gives a better visual representation of, yes, this is logistic. Now let's talk about the derivative of the logistic curve, which we have in fact already discussed. So our logistic curve looks like that. And there's x against time. What does the growth rate look like? Well, the growth rate is very slow here. It's almost, x is hardly increasing as it's just getting started. And it's also very slow, very small at here. The growth is coming to a halt. And the growth rate is a maximum here in the middle. when, you know, it's really taking off and before it started to turn over and slow down again. So the derivative of this looks something like that. And that is t1 half. So that's t x dot. And I said we've already seen this because we mentioned it in connection with the pandemic cases. So this is the total number of people who've been infected, the total number of cases, and this is the cases per day. So cases per day comes to a maximum and then falls away again. The total number of cases, the cumulative number of cases increases, but it increases at a slower rate and eventually plateaus when pretty much everybody has been infected. So that's the logistic and that's the growth rate. Well, I'm now going to talk about the idea of pseudo-logistics. Because pretty much anything that rises and falls like this will give rise to something that looks very similar to a logistic. So this is the exact form for the growth rate of a logistic, but we can replace it with things that are similar to it, and I'll show what we get. So cumulative, and here that log of f over 1 minus f. Okay, so if we have something that just rises and falls like that, it's just like kind of a semicircle or the top of a parabola or something like that, just rises and falls like that, then we'll find the cumulative growth looks something like that. It increases to a maximum, and then it declines back to zero, If we plot log of f over 1 minus f, we get something that's kind of mostly a straight line, but it tends to bend over at the top and bottom. So it works best in the middle. But whereas for a true logistic, this would be a straight line all the way. With a pseudo-logistic, it will, you know, we can kind of notice the bending at the top and bottom. But on the whole, it looks logistic. If we kind of hide that data, you know, or ignore that data, it looks pretty logistic. We can just do straight lines, go straight up and down. And again, if you actually plot this, you'll find you'll get something that does look to the eye very much like a logistic curve. And again, if you plot the log f over 1 minus f, you'll find something that's pretty close to a straight line, though you know the main deviation you'll notice is at the ends. And lastly, and sort of the most interest, because I'm going to develop this one a bit in a moment, is part of a sine wave. Now, this is actually not, well, the sine wave has been shifted up, because as we know, a sine wave goes from maximum positive to maximum negative. This isn't going into the negatives, it remains always positive. So we kind of shifted the sine wave up. If this is actually a sine wave, we know it goes between 1 and -1. So if we add 1 to everything, it will go between 0 and 2. So that's what we've got here. So if we have a shifted sine wave, if you like, then again, it looks very like that. Plots the cumulative, it will look very close to a logistic, and plot the f log f over 1 minus f, you get a straight line as for logistic, again with some deviation, most noticeable at the extremes. So going back to this, I said it's a sine wave. Well, in fact, it might be better to regard it as an inverted cosine, because we know that the cosine curve looks like that over the course of a cycle. So what we have done is we have flipped that over to get that. So we've taken minus the cosine, and then we have shifted it up by 1 to get that. So that is what that is. So this is something like 1 minus cosine of, this is against time, so it's 1 minus cosine of omega t. Okay, I'm now going to talk about a link between logistics and cycles. So let's imagine a quantity whose cumulative growth looks something like this. It's a series of logistics stacked one on top of each other. And this could be something like the economy, that we see times of boom and bust. So here the economy is growing fast, that's a boom, and then there's very little economic growth, it flattens off, that's a bust. And then there's another boom, economy growing fast, and another bust, it slows right back down almost, or back down to zero, and so on. And we know that if we plot the growth rate, the derivative of this, we'll get something that goes up and down. And we said that we can have these pseudo-logistics, and when we're seeing a cycle, we think in terms of sines and cosines based on our work on oscillation. We know that sines and cosines give rise to these cycles. So, and we've also seen that sines and cosines can be these pseudo-logistics. So here is, in fact, a cosine wave plotted, and it represents the growth rate of this. So this is a pseudo-logistic, so this isn't a true logistic, but it behaves very much like a logistic. And as I just mentioned, if we plot this, or even using that log of f over 1 minus f, it comes out pretty close to a straight line, apart from some of the extremes of the data. So it looks very much like a logistic, and we could if we're seeing something that looks logistic, it could well be being driven by a sinusoidal oscillation beneath it. And I said that this curve is not just a cosine, because it's shifted up and it's also flipped over so that it starts at 0 and it never becomes negative. So if this has the equation of, in general, A times 1 minus cosine omega t. So the 1 minus cosine omega t, the 1 shifts it up, the minus flips it over, and then we just multiply by A, because the the height is not necessarily 1, it could be, well, it's it could be A, or in fact it would be 2A here, if that's the formula, because when cosine of omega t is minus 1, this would be 1 minus 1, which is 1 plus 1, which is 2. So 2A would be the height of this. So, we see something like this and we think, sinusoidal cycles. So we might have some variable that is cyclical, like this, and that is what is its cumulative value is producing this series of logistics. So let's call this variable, which I put here is just the growth of that, but let's call that y. So there's some quantity which is cycling like this, and its cumulative value, so that's the integral of y dt, will then look like this and will produce our series of logistics. Well, we can then ask, well, why does y follow this cycle? And if we can answer why y follows a cycle, then we can explain why we've got these logistics. Well, we looked at a couple of ways that we can generate cyclical behaviour. One is direct. The other was this indirect way where we have two variables that are linked in a particular way, which was if x dot equals alpha times y, and y dot equals minus beta times x, we saw that that will give us a sinusoidal oscillation, because if we're focusing on y, we can say y double dot equals minus beta x dot, which equals minus alpha beta y, because x dot equals alpha y. So if we put that alpha y for this x dot, we get alpha beta y. We also had the minus sign, and we can write that as minus omega squared y, where alpha beta equals omega squared. And the reason we do that is because we know that if that's omega squared, then that is the angular frequency of the oscillation. So that's how omega is related to the original constants. It's omega is the square root of alpha times beta. So if we have this equation, then y double dot equals minus omega squared y, we know that gives a sine and cosine wave, gives an oscillation. But here we haven't got a plain old sine or cosine wave, we've got this 1 minus the cosine. But we can get that if we just make a slight modification to these equations. If we put x dot equals alpha into not y, but y minus a, and we keep the equation y dot equals minus beta x, then we can do the same as before. We'll just differentiate the y dot again to give y dot equals minus beta x dot, and then we've got here the value for x dot is alpha into y minus a, so this becomes minus alpha beta into y minus a. So we've got just an equation for y double dot in terms of y, and we can write that as equal to minus omega squared y minus a. Just redefining alpha beta as omega squared. So I said that if we had started with these, this would be the equation that results. Well, what we've seen is if we start with these, we get y double dot equals minus omega squared into y minus a. And what I'm going to show then is that this equation satisfies that. So we've got y equals a into 1 minus cosine of omega t. Y dot equals, well, let's just write that out. That's a minus a cosine omega t. So y dot, the constant, disappears, and we're going to have minus a times the derivative of cosine omega t. Well, the omega comes out and cosine goes to minus sine. So the minus sign, we've already got a minus in front, so that will now become positive. And so we'll have a omega sine omega t. So as I said, the cosine goes to minus sine, but the minus cancels with this minus, so we've left without a minus, and the omega comes out. So you got that a omega sine omega t. And then y double dot equals sine goes to cosine, and the another omega comes out. So we just end up with a omega squared, cosine of omega t. And that's y double dot. And now let's just have a look at this minus omega squared into y minus a. I'll put that here. Minus omega squared into y minus a equals minus omega squared into y is a into 1 minus cosine omega t. So it's that. So it's y is a minus a cosine omega t. That's y. This is what we've assumed for y there. Minus a. Well, the a and the minus a cancel. We've got a minus sine omega squared times now just minus a cosine omega t. So the minus signs cancel, and we're just left with a omega squared cosine omega t. And that is what we said y double dot should be. So this equation for y satisfies this equation, y double dot equals minus omega squared y minus a, and that equation comes from this. If we've got two variables that are related in this way. So the point being, if we see in our socio-historical data some kind of stacked logistics, we say, pulses, cycles, or some kind of cycle. We've got a variable that obeys this kind of cycle, shifted up a bit and inverted like that. And we know that we'll get that curve if y is related to some x by equations of this kind. So we then start to look, well, what are our variables x and why are they related in that particular way? And then once we've satisfied ourselves about that, we then explained why we get that form for y, and we then explained why its cumulative value is a series of logistics. And here I've assumed that the fluctuation in y always goes back to 0. So we've just shifted up the cosine so that it just touches the time axis here. So it always goes to 0. But that might not be the case. We could have, in a more general case, a sine, a cosine, sine curve that looks sort of more like this. So it's always positive, but it doesn't go back to 0. If we write the amplitude there as b, it oscillates around the value a, and it goes plus or minus b. So this formula would be it would be, let's see, a minus b cosine omega t. In that case, how would our growth look? Well, it would still, peak here, and it would be smaller here, and it would be peak here. So it would be small, a low growth rate, and then a higher growth rate, and then a lower growth rate, then and a higher growth rate, and a lower growth rate, and a higher growth rate. But because this doesn't go back to 0, but remains somewhere above the axis, then when it is slow, it's not flattening off, it's still going up, so there is still some positive growth rate. So it's faster here and it's slower there, but it doesn't flatten off completely. So what we're seeing is a kind of snaking around an overall growth rate, and it kind of speeds up above and then goes below, and that speeds up and goes below. Unfortunately, I haven't drawn that straight line through it very carefully, but yes, so what that should be is it's snaking around this trend line, and that's probably more realistic as what we'd actually see by and large, rather than it completely flattening off. And this equation here will also satisfy this, and you could just do the same as here, substitute in, take y equals that, take the second derivative and compare that with minus omega squared into y minus a. So that is also a solution of this equation, a more general one. Okay, when we were talking about cycles, we looked at the idea that a cycle can be divided into 4 kind of natural phases that we can label in terms of the seasons of the year, according to whether they're positive or negative, and whether they're growing or shrinking, or increasing or decreasing. Well, Theodor Modis, who's done an awful lot of work on logistics in socio-historical data, has suggested that there's a similar sort of natural division into phases of a logistic growth. So he labels them: the birth is when it gets started, then the phase of growth, then maturity when it's grown fastest, and then a phase of decline as the growth rate's decreasing, and then death when the growth rate has gone back to 0. So systems that go through a logistic growth may induce different feelings or have different emotional value connected with the different phases: birth, growth, maturity, decline, and death.